Hey guys, welcome to what I'm going to be calling my physics IA, let's say commentary. So basically I'm going to be reading through my IA, highlighting aspects that I think are incredibly important and aspects that you guys can learn from what I've included and what I did. So personally, I got a 20 out of 24 for my physics IA, which was a 7, and actually it dragged me up. It dragged up all my paper 1, paper 2, and paper 3 because that was the best I performed out of all of them, so nice and helpful to get my 7 in physics. But anyway, let's get straight into this. Not going to waste any time. If you somehow still haven't seen my other video going over the whole physics guide and talking about what the guide says about how to do your IA, I'm going to be drawing a lot of information from that, so make sure you've seen that first. But without wasting too much time, let's get straight into this. So let's go. So of course there is a title, nothing crazy. All right, the introduction, this the rest gets interesting. Now, I was joking with my friends, joking with my mates that when I submitted it, that my IA started with, whilst taking a bath. Okay, this is how it is. If you read it, I was trying to get some personal engagement. Honestly, when you read the whole paragraph, to me, it sounds good. To me, it doesn't sound too cringy, it doesn't sound too bad. I might have gone a little bit too far, but honestly, I think that I did well. I think that I managed to figure out a way. Because essentially, if you don't know what I did, is that I had a long PVC tube, and I filled it up with water, and it had a small hole in the bottom. And essentially what I was saying is, like, picture this, when the tube is really full, the water is going to go really fast, so it's going to decrease its height super quickly. Meanwhile, when the tube's almost empty, and the water's only going to just drip out kind of thing. So I was thinking, well, what's a real life application? Because they want to see real life application of your data, of your IA. You can't just say, this is my IA, that's perfect, and there you go, that's it. You have to always relate it to real life applications, and you have to show real world, how it can impact the real world, and particularly you. Don't forget that whenever we go to personal engagement here, it reminds you that it needs to be significant to you, personal significance. So of course, I said, well, I take baths very often, and I noticed that when it's full, the water goes out really quickly, whilst when it's empty, the water only just dribbles out slowly. So that was my personal engagement. And by doing so, I was like, well, actually, I realized this. However, I later discovered this was due to gravitational potential energy going to kinetic energy. So what I was saying is you have to show that you're in love with physics. You have to make it sound like you absolutely adore the subject. You might not. But the markers don't really care. It's about the tone that you bring across, okay? So you want to make sure you make it sound like that you adore whatever you're studying. So I can say this became particularly fascinating to me when looking at problems involving the time required to fill a tank with a leak. Now, I've actually done a lot of this in maths, but I thought it'd be something interesting to include, showing that even though, I said that to ensure I could aptly investigate a topic within this paper, I decided to purely focus on the height and time, because I mentioned later on that this was beyond the scope of my paper, beyond the scope of my IA, because I had to only write it within 12 pages. Something I found really good, or at least what I think worked out well, is that you say, this is what I'm interested in. However, because I only have 12 pages, to make sure it fits within the scope of my IA, I'm only going to do this much of it. And so this other part, first of all, you can put in your conclusion with the extension section that I'll talk about later on, but also show some personal engagement because it shows or makes it sound like you're really, truly interested in that topic. So if you continue, something else I want to point out is that you want to try and relate the topic that you're doing within your IA to a topic within the syllabus. Super simple. So I said the main physics concept is fluid dynamics. That's it. And then you should mention a real life application. I mentioned it before with the bath, but that's not exactly right because it's not a cylinder, it's more of a rectangular shape. But anyway, make sure you include a real life application of where this knowledge can be found and where your knowledge that you get from your IA, why is this useful? How is this going to have real life implications? So make sure you include real life applications of your IA. And next we have the derivation. For the derivation, you must derive it from principles. So you must derive it from Newton's first, second, third law, something that we learned in physics, but you have to derive it from background research. So I started with F as MA, and then I ended up, you can see through loads of a derivation like this shows background research, because this is slightly beyond the scope of the physics syllabus, but it's not too hard. It doesn't have some funky maths that we don't have, that we haven't done, but it just teaches us new theories, new formulas that we haven't included. So I mentioned Torricelli's theorem a few times, which shows that I've done some personal research that I actually enjoy, understand, and truly like to go beyond the scope of what's within the physics syllabus. So it shows Torricelli's theorem, and then it's also nice to include some assumptions if you need them. So within my IA, especially within this derivation, there are a lot of different assumptions, and a few of them are really simple. For example, saying that the acceleration due to gravity is constant throughout the experiment. Obviously, because the change in height is only about 20-30 centimeters, it's not going to make a huge deal. However, if the tube was, say, 5-6 kilometers, that's completely different. It sounds incredibly obvious, but they like seeing, or at least I would believe, I guess that they like seeing these assumptions because it shows that you're thinking, it shows your thought process behind it, and it shows that you're analyzing all the different significant factors that may influence the relevance, reliability, and sufficiency of the collected data. So that is what I mean when I'm talking about assumptions. Assumptions are incredible. Definitely include as many assumptions as you can. Or not as many, but include loads of assumptions. No question. Then I did my derivation. I created a nice diagram and illustration. So it was a very clear what my IA was. And yep, that was a bit of me procrastinating, but not gonna lie. But it was definitely still fun and I think quite useful to have a diagram. You don't have to do something like that. I just made that in Illustrator. It literally took me 30 minutes. I think it worked out quite well. So you need a hypothesis. After all, it's a physics IA, it's physics. Of course, you're going to need a hypothesis. And yep, nothing too incredible here. Alrighty, now let's talk about the experimental variables. This is how I personally decided to lay it out. I saw another sample IA on the physics teacher support material, and I really like how they did it. So of course, don't have to copy me, but I'll link all the other physics teacher support material as well. That scored really highly, so I decided to go really similar to what they did. So you want to separate, or at least I did, I separated the independent, dependent, and controlled variable. So for the independent variable, which is what's constant throughout the whole time, it was time. And I said, okay, how am I going to measure time the most accurately with the most precision? So I said that I decided that the stopwatch should not commence when the water was first released, as the finger may have impeded water from escaping initially, as well as the unreliability of human coordination. Now, again, this relates to all the factors that may influence the relevance, reliability, and sufficiency of the collected data. And this all relates to that one particular topic. Basically, all of this is for that one section. This makes me a bit overboard, a little bit extreme, but honestly, I think that this was worthwhile. And it shows that you really understand everything that's involved within an experiment, everything that's involved within an IA. Once again, for the dependent variable, which was the water level in my case, I said how the meniscus, which again, you need to include scientific language, stuff that's only used within a physics or within a scientific context. And so the meniscus and parallax error would have provided imprecise results. And don't forget, do not confuse imprecision and inaccuracy because they're two completely different things. You do not want to get them wrong in your physics IA. Now if we keep going, then I have my controlled variable. Same, talk about how I controlled it. And this might have gone not too overboard, but I think I definitely dived into this quite a lot. So I talk about how the viscosity of the liquid must stay the same, how the temperature of the liquid must stay the same. I also cited a paper where they found out that the temperature and viscosity of a liquid were related. There was some sort of relationship there. Then I also talked about how the dimensions of the pipe were constant, how this had to be taken indoors to reduce any wind, small things like that. So you want to make sure that you include all of the things that you need to do to control your variables. Now let's go on to the method. And you definitely need a photo of your setup, but if you can, I would strongly recommend doing a diagram just because it looks more professional, looks more scientific than if I just had that photo there. And of course, you can annotate those photos. Remember, there's no word limit, so you can put annotations wherever you want. There's only a page limit of 12 pages, which I very just got to. And also, unlike other IAs, you don't have to do double spaced. So the IB clearly prefers, or at least it sounds like that they prefer having double space within every one of their documents and every one of your IA. But this one, I think it was 1.25 or 1.15. If you can, of course, do 1.5 or even double space. But if you're really short for space, just chop it down. Don't make it single though. That's the only one thing I can say. Don't make it single space. That looks like then you're really cramming for words. Remember, in the marking criteria, it says that has to be concise. So if you write single space, or if you go over 12 pages, immediately you're losing yourself at least 1 or 2 marks. So please don't do that. Just chop down some words now and then, and at least make a 1.15 if you can. So if we keep going, we can see that here I have my method, nice and simple. And now preliminary work. So I talk about the methodology. I talk about why I chose the cylinder I did, the material, why I picked the size of the hole. So these are all things that you have to think about within your research. This shows, first of all, personal engagement, because it shows that you've actually spent a lot of time thinking about your IA. And secondly, it shows that you understand all the different aspects involved within an experiment. For example, let's look at the hole size. I said I needed an adequate size to ensure the majority of the water was released within the 60 seconds recorded, producing a large range of results. Because think about it, if I drill the hole way too big, then all the water would come out within 10 seconds and I only have 10 seconds worth of data. Meanwhile, if I'd had a small hole, really tiny, it would have gone over 5 minutes and that would have taken way too long. I couldn't have done 10 trials. So I had to find somewhere in between where I decided that I wanted most of the water to flow out within the first 60 seconds. So 1, I had a lot of data points, and 2, I could repeat the IA and the experiment very, very easily. So I said that this allowed me to record 30 data points, one every 2 seconds, which is more than sufficient to determine the validity of the hypothesis. So I mentioned it in the other video, but you need at least 4 data points, but clearly 4 is the bare minimum. Get as many as you can. I went 30. I went for 30. The more you can get, the more you can do, the better it is. So I included a lot of formulas and a lot of rearranging of formulas just to show that I had a conceptual understanding of how to work formulas, and especially within the linearization aspect that we'll look at later on. But I include a lot of formulas. After all, it's a physics A. You need to show some physics knowledge in there. Now we look at the experimental design, which is really just how I decide to run my my experiment, which is I decided to undertake 10 trials. Why? Remember that you have to justify every single thing you say. You can't just say, I took 10 trials. That's nice, but why? The marker wants to know that your reasoning behind every single decision you made. Hence why I included why I decided to make the hole so small, why I decided to make the pipe so big, why I decided to use a PVC pipe and not a see-through pipe. Small things like that. So let's read it. I decided to undertake 10 trials to increase the accuracy of the average, as the data will be less impacted by random error of any one particular measurement. So remember, do not also confuse random error and systematic error or other types of errors that are there. You want to make sure that whenever you talk about error, don't just say error is involved. Talk about which type of error. There's just these small things involved. And here we go. However, due to the risk involved and lack of accuracy in measuring the range, I've chosen the method outlined above. So what I'm saying here is that I had 2 methods of measuring the change of height of the water level in the container. So I had method 1 and method 2. Method 1 is the one I used. However, I also thought about method 2. And I gave a brief outline of method 2 within this paragraph if you want to have a quick read. So I gave a brief outline, and then I was like, well, actually, I didn't choose it because it was risky, it was hard to measure, and would have provided inaccurate results. So there are 3 reasons, though. It shows and gives a justification as to why I chose the method I did. So make sure you guys include the justification as to why you chose the method that you decided to use. Now, also include a risk assessment, because do not forget that here, they want to see a full awareness of the significant safety, ethical, or environmental issues that are relevant. I only had safety issues, I had no environmental issues whatsoever, or ethical, nothing even close to it. So a risk assessment was good. However, thinking about it, I could have probably included a bit more. So it's just these small things. I probably would have added that a little bit, considering that it makes up a whole section of that mark band, but that's all right. So you live and you learn. Next, data analysis. Okay, so this is once I got my results, which by the way, I put all on the appendix because it doesn't really matter what the results are. I just put them there in case I wanted to check my maths, check my physics. So what I decided to do personally is that I included a exemplar calculation to show that I wasn't just putting this into Google, putting this into Excel and bang bang, which I did, but I also wanted to show that I actually understood what was going on. So I said when t was 2 seconds, this was a formula I showed within my introduction, within my derivation. So this was the height that was measured. And I'm like, wait a second. Then you have to do some error propagation, which we're going to talk about later on. So the experimental error is the maximum height minus the minimum height divided by 2. And then the other error was half of the smallest increment of the measurement, which in this scenario, was the time, as the stopwatch only had a certain number of decimal places. And there you go. When t is 2, height is 0.664 with the error that is there. So guys, whenever you include a table, make sure you follow the convention. For example, here, you not only have to include the time or what the actual variable is, you also have to show how it's measured. So is it in second, is it in kilos, is it in meters, whatever it is. And then you also have to show the absolute error. So for example, or whatever the error was. For example, for time, 0.05 seconds. For kilos, whatever it was. And then small things like that. Make sure all your tables have to be nice, neat, and tidy. Spend a lot of time on your tables. Don't forget that your markers are only going to read through your IA once. They have hundreds, if not even thousands of IAs to mark individually. So they're going to just be reading it once. It's a harsh truth, but you want to make sure that they can fully understand your whole topic, your whole IA on the first go. So make sure it is easy to read, easy to understand, and the tables are nice, neat, and tidy, along with your diagrams. So if we keep going, you can see I put an initial diagram with the raw results. This was before I linearized anything, but I thought it'd be nice to include anyway, just so I can get a preliminary, I said it here, it's purely a visualization and a preliminary evaluation. And then if we keep going, then I talked about errors. So I talked about the x-axis and y-axis error bars and said that even though I did calculate the x-axis error bars, they're not even visible. So that just justifies why they're not seen on the chart. And don't forget, justification is so important. Then I talked about the root mean square error, RMSE, talk about how that was used to determine the reliability and the precision of the data. And then you linearize. Make sure that whenever you have your charts, whenever you have your data in the physics IA, you must linearize because it shows an understanding of topic 1 from the syllabus. So make sure you can definitely linearize your data. It is a good skill to use and practice before you actually do your IA. So if you still haven't done your IA yet, practice linearization for a few different formulas. Make sure it actually works because it is vital. Complete is absolutely key because essentially what you're trying to do is that you want to get results that not only are in a completely straight line, but they also have to pass through the origin and all error bars. So as I mentioned here, it says, as the line of best fit passes through all the error bars and the origin, it can be concluded that the square root of the height and time are directly proportional, which is what you want to get to. And essentially that sentence is saying that my results are correct and they are as I expected, and that they do follow Torricelli's theorem. Don't forget you have to include a maximum and minimum gradient as well as the average gradient, of course. And so what you do is they say, okay, that's nice. So it aligns with Torricelli's theorem. What else? I thought, how else can I show that my results are accurate and precise? So what I did, I said, well, wait a second. Right at the beginning of the derivation, I assumed that g was 9.81 meters per second squared. However, I thought, what about if I rearrange the formula? So I actually had to calculate g with all my data with all the data that I had collected within my IA, if that makes sense. So basically, I had all my data and I said, well, with this, let's find g. So this was a good way to determine whether it was actually a reliable IA, whether it was a reliable experiment. So essentially, here you can see that I determined the acceleration due to gravity, and then I put it on a chart, put it on a nice graph so they can see how it changed over time. And I included here a nice exemplar calculation over there. And essentially, I just wanted to compare it to its known value. So I said, from this, we can deduce that A or H0 was slightly larger. And this is because you can see here that all of the blue dots are below 9.81 meters per second squared. So that shows that something was off in my IA. Some sort of calculation I did was some sort of measurement, or there was some error that seemed to be pretty constant throughout, because see how they're almost a straight line. So what I assumed is that, okay, there was an error that was constant throughout. What could that have been? And so essentially that could have been that A or H0 was slightly larger than the dimensions displayed on the cylinder packaging, or that A was smaller than recorded. So what you're saying is that this was the error, and you justify why you believe that happened. Don't forget, you always have to justify every single thing you come to, every single decision you make. And then what else I did is that I had to determine K, or I decided to determine K, which was a constant within my IA, which was the radius of the large section of the cylinder over the radius of the small section of the cylinder. And I said, well, wait a second, now that I've got G and I've got all my data, now that I have that, I can actually calculate these two in two different ways. So first of all, I can calculate theoretically, what does the formula say that I should theoretically get? And secondly, I said, well, actually from my data, what does that say? How does my data show that my K was? So that's why I have experimentally and theoretically. And what I'm saying is that if these two things align, then it shows that my data was precise and it was accurate and it was correct. So once again, you can see that it can be ascertained that the data collected within the experiment is accurate and concords with values determined theoretically according to Torricelli's theorem. So what I'm saying is that my data was right and it was nicely done and executed. And also don't forget, within this text box, you can see here in determining K theoretically, you want to make sure you have to be very, very careful with your units, your decimal points, your significant figures, all of the above. This is stuff that not only do they ask you in paper 3, but they also really mark you very, very harshly within your IA. So don't forget here, it might look weird that my error was 0.000. However, you can see above what my exact error was. But of course, because of the significant figures and decimal places, I couldn't include anything, so it just looked like 0. So you've got to be very careful with what you include within your IAs and within your data. So now if we keep going to the conclusion, almost at the end, and then within my conclusion, basically what I was saying is that this is the theory. The theory aligns and concords with my results. And from these results, this is what we know. So I know that in my results, there were no outliers. Why? Due to the methodology being suitable, as I point out here. And also I'm like, well, why did this happen? Why was it such a good thing? And I say this also shows that the assumptions made when deriving Bernoulli's equation were valid, and all the control variables were managed very effectively. So that's what they like to see. They want to see that whatever you've done, all the variables that you chose to control were nicely managed and controlled. So if we continue, it says, therefore, this investigation proved the hypothesis and successfully answered the research topic. Because if we go to the physics guide, it says that, first of all, the background information is all entirely appropriate, but also within the analysis, they want to make sure that you come to a detailed and valid conclusion to the research question. And it takes full consideration of the impact of measurements and uncertainty on the analysis. So literally within those 3 sentences, I address all of them. So that's what you want to make sure to do. So you want to tie in all different aspects of the marking criteria within, basically throughout your whole IA, embedded throughout your whole IA. So if we keep going, what else do I have? I talk about the real life implications. Going back on this, I could have definitely expanded this a lot more, other than including baths and dams. I'm sure there's other examples of this, but let's read it out. This has real life implications as it can be applied to flood management schemes for dams discussed earlier in this paper. That's nice, but it doesn't really show any real life implication how actually this is important for me and significant to me. It doesn't show any personal significance, which is what I would change looking back on this. Now, if we continue to the evaluation, the methodology, don't forget that there's different types of error. I mentioned it earlier, so make sure you differentiate the different types of error within your IA. Talk about the limitations, so you talk about the positives and the negatives of your methodology. For example, a limitation of mine is that my IA was only suitable for a cylinder, but only when this top cylinder, when the radius of the big circle of the cylinder is much larger than the small radius of the cylinder. So it's just these small things. And I said, wait a second, how could this have been improved? Well, actually, if I'd used different materials, if I'd used a different pipe, then I could have had more accurate results, and it would have changed the significance and the accuracy. And here we go again. I say that accuracy and precision of the data was another strength. And then you have to talk about the extension. Don't forget how you can extend your IA. And remember how I mentioned earlier in the introduction, how you say, this is what I want to talk about, but I'm only going to talk about this much because I have 12 pages. This is where you talk about the other stuff, essentially. This is where you say, well, if I had the time, if this was in the scope of the IA, this is what I talk about. So here, I actually talk about how, wait a second, what if theoretically, going at Bernoulli's theorem, it states that if the height of the cylinder, is of infinite height, then the discharge of the cylinder is infinite as well. And I was saying that can't make sense. There's no way that water can go faster than the speed of light, is what I was trying to say. This is what went through my head. So there's just these small things. I'm like, wait, if that can't be right. So what I was saying is that here, it would be interesting to determine if it's applicable at any water level, even at very large values. So I said, without having studied fluid dynamics in depth, I predict that there is a maximum discharge value of the cylinder, even if there was only laminar flow. So once again, putting in that terminology that's used within a physics context. So what I'm saying is that I'm interested in this topic, I'm personally engaged in this, and I'm curious to see what would happen if this did. Would my theory, would my formula still be applicable? Or is there another consideration that I did not put in place? Is there another thing I did not consider? So there's all these small things that you want to talk about within your conclusion and your evaluation. And the extension, basically what I said is that I wanted to make mine more precise and accurate, which, thinking about it, wasn't really the best extension after all, because you want an extension to show more. You wanted to justify why you want to extend it. Don't forget, you're not just showing this could be an extension. Why is this good? You have to say why it's good, why it's accurate, and why it's required, and why it actually have real world impacts and implications. So honestly, that's the end. You can see I only just had enough words, or I only just managed to fit it within 12 pages. I found it quite tight, a little bit of a squeeze. And of course, bibliography, got a couple pages of that. And other than that, guys, good luck with your IA. I hope this really helped you out. If not, send me a message in the Discord group. I'll be sure to help you out. And other than that, good luck, guys, with your IA and your exams. Thanks for listening.